Hello. Well, this is a very interesting presentation which makes use of graph search for solving the problem of motion planning for multiple autonomous vehicles. The introduction to this presentation is taken as a different video which should be available somewhere in the video description. Now, we of course first look at what all a general graph search can do and what all it cannot do. Graph search is taken as a very assured and a very interesting kind of search which can basically do everything. It'll in general generate in the best plan, which is the most optimal plan, and if any plan exists then it will definitely generate in, so it's both optimal and complete. But of course the problem is that it is very slow, and therefore in most of the situations we cannot use it. So for a problem like multiple autonomous vehicles, it will be like it's trying to find out all unit possible moves of all the vehicles combined, and then it's trying to generate an overall optimal plan, which we know that will never come in hours. Forget about the milliseconds and the seconds that we need to cater to. So the issue is, how do we make this very slow graph search very fast? And the solution is what is in general always used with any graph search approach for any domain, and that's called as the idea of hierarchy. We cannot solve a problem, so let us decompose the problem into various levels of abstractions. We'll say this is abstraction 1, this is abstraction 2, abstraction 3. While abstraction 1 will only deal with the first degree of abstraction, will work over at a very superficial level. As we go down, we'll get the detailed view of the problem, while some kind of higher level plan will already be available, and that's how we'll solve the problem into multiple levels, into multiple hierarchies, which overall will generate the overall plan. So the issue is that I need to introduce some mechanism of dividing the problem of motion planning for multiple autonomous vehicles into some hierarchical framework. And how do I do that? Well, first of all, let us assign some definition to each of the hierarchies that we would be seeing. So let me say there is some general road like this, and there are some obstacle like this, and there may be some vehicles out here at any other place. The first definition that I'm going to introduce is called as a pathway. Well, from this very scenario, it looks at this vehicle, which is the vehicle being planned. It can travel in multiple ways. It can travel like this, it can travel like this, it can travel like this. So there are so many plans. While only considering the static obstacle, I say forget about the other vehicles, let us consider only these static obstacles. So it looks that there are broadly so many plans possible, and let me just highlight one of the plans, which is this plan. So I say I take right from obstacle 1, I take in left from obstacle 2, and I take in right from obstacle 3. This is one very general plan out here. Of course, there could have been multiple such plans. The second plan could have been for the same scenario like this. I take in left from obstacle 1, I take in right from obstacle 2, and here is my plan which is generated. So basically what the shaded area in both these graphs shows, it shows the effective road that is available out to me. It shows the effective road that I can use which does not pass through any kind of obstacle. So let me formulate in some kind of virtual boundaries which completely bound the obstacles, which are like these, and that is what I'll know it as the pathway. Another way to look at it will be, while the road has some static obstacle, let me bound the road in such a way so that there are no obstacles, and the bounded road in such a way, and there will be multiple of those possible, like we saw one here and the other one here. The other one would be like this. That would be called as the pathway. I take in one unit slice of this So let me say that I've in fact already given out the slices by the way that I was doing. So let me say that if I take in a unit slice of this would be called as a pathway segment. Another slice that I can take out is this, which of course completes which of course has the complete road. This one ended up at this obstacle, this one ended up at both the road boundaries. If I take another slice in this one, it also ends up at some obstacle. So this would be known as the pathway segment. So two terms are defined when I only consider the static obstacles and I do not consider anything else. The third definition that I would be giving out is considering the presence of other obstacles. So let me say that this was a pathway segment that is highlighted out here, and there were some two vehicles which were to occupy this pathway segment. So let me draw in an enlarged picture of this. This is the pathway segment, the same segment that we deal. Now there are two vehicles which are occupying the same pathway segment at nearly the same time. So I'll have to distribute this pathway segment in between two vehicles. So let us say the two vehicles were very similar to each other. So half of it would be used by the first vehicle. Whatever it does not matter. Half of it would be used by the second vehicle. Whatever it does, it weaves around, it drives straight. As long as it is inside this small pathway segment, it doesn't matter. So first I did not consider any other vehicle, and then I considered two vehicles and I divided the available pathway, two vehicles which were scheduled to occupy the same pathway at nearly the same time. I divided them between these two vehicles. Let us take a larger pathway. So let us say that I taken this pathway segment right here. I produce an enlarged version of it, this one, and let's say four vehicles are to occupy this at nearly the same time. One may be at a little distance, but they occupy at nearly the same time. So I divide this into four segments. Let's say the vehicle one out of those four will occupy this, second will occupy this, the third will occupy this, and the fourth will occupy this. So this is what I know what I would be calling it as the distributed pathway. Any one slice of it would be called as a distributed pathway, and that makes me very clear in regard to what would be the general architecture of the algorithm. First, of course, there's a city level, there's a city kind of map here where there's a road network graph which consists of all the city roads, all the normal roads, all the double lanes, all the single lanes that any city may have. There'll be a source and there will be, let's say this is the goal, and this would be known as the route to take. So my first problem is selecting a route. Any route that I take will be consisting of a road like this, which will be segmented into multiple road segments that we've already seen. Any such segment, let me draw an enlarged picture of it. Any such segment will be like this. Any segment would have some obstacles, static obstacles like this. So this is my hierarchy 1, which is the route selection. This is my second problem would be in finding out this kind of pathway, which more exactly is this area right here. So I'll not consider I will basically consider in how the vehicle avoids in static obstacles, how the vehicle is will be avoiding static obstacles, as in for which obstacle it will take to the left of the obstacle and for which obstacle it will take to the right of the obstacle. So basically I'm designing an obstacle avoidance strategy as my hierarchy 2. Now my output of hierarchy 2 will be with this nice little graph out here. So after my hierarchy 2 output, I do not need to consider about static obstacles in any way, as long as I am inside this pathway. As long as I am inside this pathway, I can never collide with a static obstacle. So let us now extend this algorithm to hierarchy 3. My third level of hierarchy would say, suppose I take in a thin slice of this obstacle segment, which is this. I'll see how many vehicles are to occupy the segment, say 3. So I'll distribute the vehicles between these 3. I already know which vehicles are to occupy this at the nearly the same time. So I'll distribute the segment and produce in my hierarchy tree the distributed pathway, and like this I should take one by one all the suppose one of the vehicles is very fast, it leaves here. When vehicle 1 is here, it's only left with vehicle 3. Suppose later it's the vehicle 3 leaves behind, vehicle 1 is fast, so it's only left with vehicle 1 at this pathway segment. Later on there's a vehicle from the other side which is coming, which is vehicle 5, and so it's vehicle 1, vehicle 5 at this pathway segment out, at this pathway segment out here. So this is my hockey tree planning, and what I'm basically trying to do is at every slice I'm seeing how many other vehicles are expected to be there, and I'm evenly dividing the route among all these vehicles. So very if you see at this level of abstraction, what I'm doing is that I'm creating snapshots of a traffic. I'm creating snapshots of traffic scenarios where each snapshot tells us about the lateral placements of the vehicles. The normal picture of traffic, we all know that there are too many vehicles, one here, one here, one here, one here, and one here, some vehicle here. What I'm trying to do is that I'm trying to create snapshots. Let's say at this time the traffic will look like this. At some other instance of time, it'll look like this. That another instance of time, this is how it will look. So I'm creating snapshots, and snapshots are naturally discrete in nature. Your vehicle cannot move by a knowledge of snapshots alone. It'll end up colliding somewhere, or it'll end up not knowing how to go from one snapshot to the other snapshot. So for that I have hierarchy 4. It takes as an inputs these snapshots of time of scenarios and generate in smooth trajectories for any other vehicle. So my hierarchy 4 would be trajectory generation. So very quickly, first I found out the route. I divided the route in overlapping segments. For any segments there were obstacles. So for the obstacles I said that first let me deal with only with the static obstacle, find out a strategy to avoid these static obstacles. Each of these slices I used to create a snapshot of the traffic scenario considering the other vehicles, dividing the road between the vehicles, or dividing the pathway segments between the vehicles, and then I connected these snapshots by smooth trajectories. And the vehicles can obviously track smooth trajectories by using any control algorithm, by using any trajectory tracker algorithm. They can track these smooth trajectories that my level 4 hierarchy produces. I'll once again very quickly repeat, because this is effectively the entire algorithm. Once you understand the hierarchies, you understand everything. Hierarchy 1 I've not shown here. It's common for all the algorithms that I've been presenting. It starts with hierarchy 2, which is of course the obstacle avoidance strategy. What is the aim of this strategy? Well, everybody wants to drive in such a way so that his distance from the left and right boundary is the largest. So one tries to drive at the center, and if there's an obstacle, one wants to drive at the widest of the possible ways of avoiding the obstacle. And that's very natural in human driving. If you look at how you overtake a vehicle, you try at any instance of time to keep the maximum distance possible. How do you avoid the obstacle? You drive straight in the middle of the obstacle free region, because efficiency is regarded by which route you take, how much congestion it has, and all these factors. Efficiency is not regarded by your lateral movements in very broad sense. So you try to prefer safety over efficiency, and safety means that you select the widest road, so that even if you weave around here by some duration, even if you skid by some duration, it does not matter much. You've got so much of room to do that. So the objective of pathway selection would be to find out the widest, and of course some odd looking pathways cannot be selected. So this is my objective 1, and this is my objective 2, the shortest pathways. Once I have got a pathway, once I've got a normal strategy of avoiding static obstacles, then I come to the other vehicles, where I would again be distributing the available pathway segment between vehicles such that each vehicle has as large as distance as possible. And that's why I said that I'll be having equal division between the vehicles. I never said that if this is the obstacle, I'll place obstacle vehicle 1 here, vehicle 2 here, while the road is so much big. Now this is a valid strategy. this seems a valid strategy, but the vehicles are very close to each other. If this skids by a little amount, anything can happen. So instead, what I'll do is that I'll place vehicle 1 here, vehicle 2 here, such that the distances are maximum. So again, I'll be using the same fundamental principle that separation has to be as largest as possible. And of course, when I say that I'll be placing vehicles, I need to do two things. One, that I've already said, that I need to divide pathway equally between the vehicles. The second is, if there were three vehicles here, V1, V2, V3, I need to decide whether V1 goes here and V3 goes here, or V3 goes here and V1 goes here, or V1 goes in this slot and V3. So what will be the relative order of the vehicles? That is what I need to decide in pathway distribution. I know all the vehicles are approximately to lie at the same pathway at the same time, so I need to distribute them laterally. I need to distribute them laterally. What in the sense of driving with the speed lanes, it is known as giving them each a different lane. Here I'll be also dealing with the problem of how to decide the order, in which order do they appear. And as it would be natural, I'll be using some very natural principles to decide this order. The third trajectory, the third hierarchy deals with how to connect snapshots of time, of traffic scenarios, how to connect general obstacle avoidance and vehicle distribution strategy into smooth trajectories that are feasible, as well as it can be traced by a vehicle. If they are infeasible, or if they are if they are not smooth, then I'll need to do something known as local optimization to make them trackable. That's what my three hierarchies would be doing. Now, if it was a single vehicle, or we basically say we know how the vehicles move and we need to just plan a single vehicle, based on these hierarchies, it becomes very clear how in general my algorithm would move out. Some of you may in fact have even visualized that how the general division of hierarchy and how the general algorithm would move. The problem is, I have all multiple vehicles connected by a communication architecture, and I need to solve all of them. Now, when I say that a single vehicle needs to be planned, I call it the level of problem of planning. And when I say that multiple vehicles need to be planned, there's a concept of coordination, which basically says how the different vehicles avoid each other. Now, this needs to be implanted. In general, we are, of course, will be using something known as priority based coordination. A priority based coordination means that first I plan the first robot or the first vehicle. Given its plan, I plan the second robot or the second vehicle. The trajectory of this robot or this vehicle is known, so I can treat it as obstacle and make this robot or this vehicle avoid this one. And then that I plan the third robot or the third vehicle. Both these are taken as obstacles. I know the exact trajectory, so I can treat them as dynamic obstacle, and I decide its path. Now, the problem here is that I have got three different layers of hierarchy, and I do not say four layers of hierarchy because route selection algorithm does not consider the other vehicles. So it's basically a simple Dijkstra's algorithm, which computes the shortest path between the source and the goal to find out the route, which is divided. And after that, I have got three layers of hierarchy in which I need to implant this problem of solve this problem of coordination. This is the general principle, but this principle does not hold good when it comes to hierarchies. So how do I solve this problem in terms of hierarchies? The solution is very simple. First, let us solve all these three vehicles or all these three robots for hierarchy 1, which is my pathway selection. First, let us find out the pathway selection of the robot with the highest priority. Given its pathway, let's find out the pathway for the second robot with the second priority. Then, given the pathways of the first robot and the second robot, let's find out the pathway for the third robot, which gives me the pathway of all these three robots. Then I come to hierarchy 2, which means given the pathways of all these three robots, Find out the distributed pathway for robot 1. Given the distributed pathway for robot 1, find out for robot 2, and given the distributed pathway for these two robots as well as the pathways for all these three robots, find it for robot 3, which then I do it for hierarchy 3. So the general principle of co- coordination in a single hierarchy can be very well implanted to to the principle of coordination for multiple hierarchies, and this is what I know, what I call it as a layer by layer coordination, which means one layer sees the same layer for deciding its coordination. I solve the problem of coordination layer by layer. Now in a problem of the problem of autonomous vehicles has an additional problem, that basically one vehicle enters, it decides everything how it has to go solve its problem. After it has reached some different some point way ahead over here, then the second vehicle comes. Now while I was planning for this vehicle, I did not know that suddenly this vehicle would come up in between, and this also has decides some plan keeping itself in consistence with the this. When it's somewhere here, then the third vehicle comes. While deciding the plan of this vehicle, I did not know about this vehicle. While deciding the plan of this vehicle, I did not know about this vehicle, and this is the problem of unknown time of emergence. Well, the problem of unknown time of emergence in general can be handled very simple. I say when the third vehicle arrives, when it arrives, let us say cancel, I delete the plan of this vehicle and I delete the plan of this vehicle and plan all these three vehicles again. And that's a very fair strategy to do, that whenever new vehicles arrives in the road segment, let me cancel the plan of all the other vehicles that were planned earlier. In a road scenario, it means that if there are 10 vehicles, then I'll have to replan each one of the 10 vehicles, which is very time costly exercise. So it cannot be do. So I would be using again the same principle of layer by layer coordination as illustrated here. I'll be using the same concept, but I'll need to adapt it to this problem of unknown time of emergence. And how will I do this? Whenever this vehicle comes into the scenario, whenever this vehicle enters into the scenario, it sees that they are vehicles which may be of higher priority or low priority, but they are vehicles which have already planned their pathways, which have already planned the distributed pathways, and which have already planned the trajectories. So when I need to plan this vehicle at the first hierarchy or at the hierarchy of pathway, I see which other vehicles are affected by the emergence of this vehicle, and it might happen that many of the vehicles are completely unaffected by this new vehicle entering. So in order to illustrate, let me take a simple example. If there is an obstacle out here, if there is a vehicle which is out here, and if there is a vehicle which is out here, and then my new vehicle enters like this, it decides based on its assessment that whether this is a better pathway to go or this is a better pathway to go. Let us say it decides this is a better pathway to go. Vehicle 1 by its trajectory was traveling like this, and vehicle 2 by its trajectory was coming like this. Now I need to not consider vehicle 3 here, the vehicle 2 here. This vehicle over here will not be affected by this vehicle traveling out in this direction. By the time it arrives here, it would have already reached its destination. Say it's a very fast moving vehicle. So I'll not replan this vehicle out here. However, I will have to consider this vehicle out here. So basically what happens while I'm planning the pathway of this vehicle, I will see which other vehicles are affected. While I'm planning the pathway of this vehicle, I'll find vehicles which are affected, which have got a lower priority than this vehicle. That's very well possible. And I know that in pathway planning or in any layer of planning, I do not consider a lower level planning vehicles in my prioritized planning. Prioritized planning says that a higher vehicle, a higher level, a higher priority vehicle never considers a lower priority vehicle in its planning. So let us say this vehicle in fact had a, so let me basically say that this vehicle, it selected this route, and for now let us say that this vehicle had a lower priority as compared to this vehicle, so this completely disregarded this vehicle. Now it will have to inform this vehicle that I am coming from here, you are low priority vehicle, I have priority over you in this region, I will not consider you in this region, and therefore you need to replan at the pathway level. So only this vehicle is replanned. On the other hand, if in the same scenario I say that this vehicle had a low priority vehicle, it does consider this vehicle a vehicle in its low priority. So now obviously this vehicle will not change its pathway, it will continue to drive in the same pathway, and this vehicle will consider this vehicle in its pathway if it can, and correspondingly it will decide its pathway. But the problem is that now this vehicle still needs to be made aware of this vehicle, because now it will have to share this region between these two. That means its distributed pathway gets affected. Earlier it had complete monopoly over this region. Now this region will get distributed between these two vehicles, and therefore this vehicle needs to replan at the distributed pathway level or the lower pathway level or the lower level. So the details of this of course I'll be taking later. So the key point here is that this vehicle does not replan at any level, while this vehicle, if it has a higher priority, replans at the same level or the pathway level, and if it has a low priority, it also replans at the lower level. So the general point is what I'll be covering in detail later, that any vehicle can be asked to replan at any level. That's what from a general algorithmic architecture is a point that I need to take in mind. Any vehicle can ask any other vehicle to replan at any level. If you by chance, if you sufficiently got that point, you will understand that usually it would be a higher priority vehicle asking a low priority vehicle to replan at the same level, and higher priority vehicle will ask vehicles with the same higher, with the even more higher priority vehicle to replan at the lower level. It's basically that there's seniority at each of these hierarchies. So there are different hierarchies associated, and vehicles have their seniority out here. This vehicle can ask this vehicle to replan at the same level because it's senior, and this vehicle can ask this vehicle to replan at not at the same level because it is senior, but it can make it replan at a junior level or at a much lower level of hierarchy. So that's what I present in the algorithmic architecture. The implementation details of course will follow. I was speaking about this thing, and the other important issue and the last important issue that I will be dealing with out in the general problem of coordination is that the coordination is layer by layer. So while I plan the pathway of vehicle 1 amidst a pool of vehicles which are completely planned or which are partially planned, I'll only consider the pathway of vehicle 2, vehicle 3, vehicle 4. So while my pathway planning, every vehicle will share its pathways which will be used for the planning of vehicle 1. While I'm planning the trajectory of vehicle 1, I'll only be using the trajectories of vehicle 2, vehicle 3, vehicle 4. So it's not that I'll be, while planning the trajectory of the fourth vehicle, I'll use the pathway while planning the trajectory of the first vehicle, I'll not be using the pathway of the second vehicle. I'll be using the same thing, that means trajectories for all the vehicles, but while planning the pathway of a vehicle, I'll be using the pathways of all the other vehicles and not the trajectories of the other vehicles. So what happens is that while planning pathways, I only consider all the pathways of the different vehicles. While planning trajectories, I only consider trajectories of the other vehicles, and that's done for two reasons. Firstly, while I'm planning for pathway of vehicle 1, the pathway of vehicle 3 might not be the trajectory of vehicle 3 might not be available. It may be invalidated later on. It may be unclear what trajectory it is following. It may be scheduled to be planned later on. So I need to consider the pathway. And secondly, when I say pathway would be level by level or layer by layer, as a data structure algorithmically for practical implementation purposes, it became very clear for very beneficial for us, where the same data structure had to be used and compared across the vehicles across the hierarchies. So it became very difficult to compare a pathway with a trajectory or distributed pathway with a trajectory, but the pathway to pathway level comparisons became very different, very easy to us. The only catch here is that while planning distributed pathway, which is hierarchy 2, in place of using distributed pathway of the other vehicles, I use pathway of the different vehicles. So even though coordination is layer by layer and the same entities were being considered, only in the case of distributed pathway I consider the pathways of different layers for coordination and not the distributed pathway, because again of the data structure problem, as well as the problem that the pathways for some distributed pathways for some higher priority vehicles were unavailable. And with this, the general structure of the algorithm becomes very clear. There are clearly four layers of hierarchy, which is hierarchy 1, hierarchy 2, hierarchy 3 and hierarchy 4, which generates a trajectory which the controller can generate. Any hierarchy, any vehicle or any hierarchy can ask any other vehicle to replan. Now this is only one vertical that I have shown, which may be for vehicle 1. There may be similar verticals for vehicle 2, vehicle 3 and vehicle 4, which I have denoted in short by here. Replanning means different vehicles are asking each other to replan, and because for the selection I do not need to consider anything of the any other vehicle, but as the coordination is layer by layer, for the pathway selection and pathway distribution I consider the pathways of the other vehicles. For trajectory generation, from the point of view of coordination, I consider the trajectories of the other vehicle. So this is broadly what the algorithm is all about. This is broadly the architecture. I'll first present the results, and then I'll go into the intrinsic details of the different layers of hierarchy. The major parts of the algorithms have been covered, so after the results many can switch off the video. And here we see that the route selection algorithm and how the vehicle places itself in the center. Obviously, a single vehicle always keeps the maximum distances from the obstacles, which may be very clear from all these examples out here. As well as when there are two vehicles, they keep the maximum distances between each other. This is when they avoided each other, and this is after avoidance, and even before the vehicles were individually trying to keep the maximum distances. The places where you do not see the maximum distances are because it became very difficult to it became very steep to take such kind of route, and hence in optimization we allowed the gaps to be reduced when there was sufficient amount of certainty that reduction in gaps will not matter much. And that's for the other vehicles. This is a critical scenario where one vehicle plans to keep at one side and the other vehicle to keep at the other side of the obstacles, rather than both vehicles trying to go at the same side. And again, you see the vehicles avoid each other with large gaps and keeping large separations from the obstacles, which is why this vehicle effectively took in this nice little turn out here. For a multi-vehicle scenario, the same thing takes place. The vehicles are nicely avoiding each other. In this case, they are even timing each other well, so that they do not come up at the same time at the same place. In a lane-like scenario, the vehicles, they obviously they try to select the widest pathways. These would be considered the obstacles, and hence they try to schedule themselves at different lanes rather than all the vehicles taking this very short lane, which is in general more preferable. And then we've got the overtaking scenario, where this vehicle overtakes and this vehicle cannot overtake anyways, and then as soon as it can overtake, it succeeds in overtaking, all by these four layers of hierarchy. The different results that we have shown, they highlight the working off the different layers of hierarchy. In some scenarios, pathway selection was very important, in the other pathway distribution was very important. So all those have been highlighted in the results. So now we come into the intrinsic details of the various layers. I'll try to keep it as simple as possible. The first is the pathway selection, and how do we deal in the problem of planning of multiple vehicles. I first plan for a single vehicle and then I generalize the algorithm for multiple vehicles. So the problem is that I have got some obstacles like this. Because I'm considering only a single vehicle, there's nothing else involved. What I do is that I use the concept of sweeping line, wherein I say that let me have a sweeping line go through everything like this. Now in every line, in every such line drawn, I basically ask the question, where would you like to place yourself? Here there is no obstacle by distance maximization theory, I'll place myself here. Here I'll place myself here. Distance maximization theory, here I'll place my here. Here if I need to avoid from left, I'll place here. If I need to avoid on right, I'll place here. Here separation maximization, I'll place here. Here I can place myself in any of these three situations. Here of course I'll place in myself here, and I form this nice little graph. Now all the edges, this edge is not possible, it seems very likely, so that is what I draw. I've got a nice little graph out here which underlies what a single vehicle would see, and then I basically got the problem where I need to decide a way to travel out in this graph, and I need to select the widest pathway, and the widest pathway means that it passes through the widest areas. That was my objective one. Now if I take anything like this, the problem is that it goes through this region and this is not wide enough. If I go through like this, the problem is it passes through this, and in fact this is smaller than this, so again this is not wide enough. So what I'll basically do is that I'll pass through this. The most narrow segment is this, and this is indeed wide enough, so this is what I would be selected. In case in case this made the road very long, then the second, which is wide as well as short, would have been selected. So that's what I would basically be doing, and I've got the same picture, nice little picture out here, which basically does the same thing. The important these ones are the sweeping lines out here. This is what the sweeping lines are out here. The gray region is what is the pathway, so you can nicely little track this pathway which the vehicle would be following. This is what, as I said, this is the obstacle free road or the pathway that the vehicle would see. So after this nice little blue segment is up, the vehicle need not consider any of these obstacles. This should be like this. This would be blue one is my pathway. For computation purposes, I cannot work with this area of this colors, and also for algorithmic purposes what we've done is that we keep a track of these points that we were marking previously, which will be known as the pathway segment end center, because it is at the end of the pathway segment. This is the pathway segment and this is the end and this is the center. So that this is one point that I'll be making note of always, which is the pathway segment end center. And of course these are the pathway segments which are nicely given by the sweeping line. For computing the optimal pathway, which is this blue region out here, I use the Dijkstra's algorithm that finds in the widest, and if there are too many wide segments, in the widest and the shortest pathway, and all the other lines have been denoted by this red color. So that's for a single vehicle. The problem is that now I need to extend my planning algorithm in hierarchy 1 from a single vehicle to multiple vehicles. So again, let me take in the same scenario here, some obstacles out here, and of course we know by the basic terminology that I'll need to follow in the same principle. So I'll again be having a sweeping line cover out here. Now, what do I know from the other for the other vehicles? I know that I am a vehicle here which needs to be planned. I also know there are some other vehicles out there. Some of them have a higher priority, some of them have a lower priority. So basically, in my terminology, I am this vehicle V out here. There are vehicles V1, V2, and V3 which have got higher priority, and there are vehicles V4, V5, and V6 which have got lower priorities. For all the higher priorities vehicle, the pathways are already available. I know the pathways because even if there were multiple vehicles to be planned at the pathway level or at the hierarchy 1, always the higher priority vehicle is planned before the low priority vehicle. So the pathways of all the higher priority vehicles are known, while the pathways of low priority vehicles may not always be known. So I obviously start selecting points again like this, but this time when I select a point like this, I ask one question. I basically ask two questions. How many higher priorities vehicles are expected to lie in this region around this pathway segment at approximately the same time that I would be expected if if I choose this pathway segment for my travel. So I'll repeat the question. The question is, how many higher priority vehicles are expected to lie in the same pathway segment or near the same pathway segment at nearly the same time when I am here at this pathway segment, if I choose this pathway segment in my planning, if I choose this pathway segment as the optimal pathway. And similarly for the lower priority vehicles, how many lower priority vehicles would be here? Now of course, I can only say for the low priority vehicles whose pathway is already known. So for the higher priority vehicles, I know that while planning my pathway selection or while planning hierarchy 1, I do not need to consider the low priority vehicles, because that's as per the prioritization principle. A higher priority vehicle never considers the low priority vehicles. So I need not consider these, but I need to consider the higher priority vehicles. And what I say that, suppose the answer is that there is one vehicle which will be here at nearly the same time, at nearly the same place. So there's one other vehicle which will be here when I'm approximately here. That is what I can find out using by interpolating the movement of the other vehicles out here. So let me just say that my vehicle 1 was actually moving like this. It's here, it's moving like this, and while it is here, it's let's say it's a very fast moving vehicle, so it reaches here at the same time that my vehicle 1 plans to reach here. So they both move at the same time, while there was some other vehicle, let me say that it was vehicle 2, which started its which at the present is here, and it's trying and it's planning to move like this. So only vehicle 1, which is this vehicle out here, it is by its projected motion at the pathway level. Now remember, the actual motion of this vehicle might be very different. It will obviously never be at the center of all the lines that I've tried to draw out here. I have projected this motion to be traveling like this, like it would be traveling in the center of its pathway, or it's joining the pathway segment in centers. I have projected this motion here. I have visualized this vehicle traveling here. In fact, what you can do immediately is that I've only shown 2 vehicles out of these 6 vehicles that I considered. You can try visualizing this vehicle moving very fast from here to here, and this vehicle moving quite slowly from here to here, while this vehicle moves from here to here. So in this visualization, if you see that if this vehicle collides with this vehicle and this vehicle does not collide up with this vehicle, So the answer to my question that how many higher priority vehicles, this is how my question that how many higher priority vehicles are expected to lie in this region, this is how it gets answered. And similarly, this is how it gets answered how many low priorities vehicles are expected to lie in the same pathway. What I do is that I think that this is the width that is available to me. There would be one vehicle out here which can be driving anywhere in this pathway segment. So let me say this is that yellow vehicle out here. It will have some width. It will need some separation. So let me say that W is the total width that it will occupy. And there is, because it's a high priority vehicle, there is nothing that I can do about it. It will occupy this. I'll say that in whatever remaining width is available to me, can I fit myself in? And if indeed I can fit myself in, then this is a valid pathway. This can be used. Now, suppose that I do the same thing, but instead I have a different pathway segment here. I ask the same question for this pathway. If I drive somewhere like this, how many higher priority vehicles will I get and how many lower priority vehicles will I get? The answer, suppose it's 1. Suppose this vehicle reaches at approximately the same time that this vehicle reaches, and this vehicle needs this much amount of space. Now I say that how much amount of space is available? It's very little. Will I be able to fit in? The answer is no. I mark this pathway as blocked. So basically this is a valid pathway, two vehicles that are scheduled to be at the same place at the same time, nearly the same time. This is a valid pathway, whereas this is a blocked pathway because I have a vehicle of a higher priority which is still here. The other issue is that if this vehicle had been a lower priority vehicle out here occupying the same pathway at the same time as this vehicle, now I wouldn't have asked the question that this vehicle needs this much amount of space, can I fit in? Because clearly in priority based planning we do not consider the low priority vehicles, we only consider the higher priority vehicles. So that's how I do it for all the pathways. I find out which are the valid pathway, which are not the valid pathway. Let me take another example of a very wide pathway, which is this pathway. Now I'll not show V1, V2 and V3, but suppose there are 3 vehicles which are projected to lie at the same place. So I simply add up their widths. Let's say this is the width for W first vehicle, this is the width required for the second vehicle, this is the width required for the third vehicle. If I still have space to fit myself in, then I'll say that this is a valid pathway, else I'll say that it's blocked, and by the way, this blocked means the entire road is blocked at the current moment. So that's how I'll basically done the pathway selection at this level. To very briefly summarize, I know how many vehicles would lie at a particular pathway segment. If I select the same pathway, I consider only the higher priority vehicles, and I ask myself that given these vehicles will be here, I cannot do anything about it. Can I fit in the remaining width that would be available to me? If I can fit in, I will select it, else I'll mark it as blocked. So in the previous slide that we see, if we in fact did consider multiple vehicles, something coming here, something coming here, and we visualize each of the motion, many of these pathway segments would get blocked. In the modified graph, I'll use the same search. So that was about the planning of this vehicle. For now, in the same example, consider that I still have my yellow vehicle out here which had the higher priority vehicle and I could nicely fit in. Now
because this yellow vehicle knew nothing about anything before. It knew nothing about this vehicle being here. It would have planned to occupy this space, while now this segment would be evenly distributed between a red vehicle and the yellow vehicle, or it can be the red vehicle here and the yellow vehicle here. I need to inform this to the yellow vehicle that now you cannot occupy the center of the road. Now you need to move in at some side, either left or right. So the yellow vehicle, which means the entire set H of higher priority vehicles, would be replanned. They would be replanned at hierarchy 2, or the pathway distribution, while if I used this segment out here and this vehicle had a low priority vehicle and this was a low priority vehicle, then obviously I'll use this vehicle. I do not consider the low priority vehicle, but now I'll have to inform the blue vehicle out here that I am coming through this region. You better look at it that after I come into this region, whether you will be able to occupy, whether you will be able to travel here or not. If you would be able to travel in this region, more than welcome. We'll both share this region. If you cannot travel, then you better need to do something else. So I'll need to plan the lower priority vehicles. I need to replan them at the same level, at hierarchy 1 or at the hierarchy of pathway level. Again, only those vehicles which were returned in my search query and those vehicles which came in the path segment, which was the optimal pathway, would need to be planned. So I basically did not tell here that I'll be using either this or this. If I use this, then only the H is planned. If I use this, then only L is planned. H is not replanned, because clearly if I use this, the yellow vehicle does not get affected. So only those H and L which come in my optimal pathway would be replanned. And the last level to deal with, which is very important, is how do I design a prioritization strategy. The problem here is that I need to design the prioritization strategy keeping the general driving principles and keeping the general traffic rules alike. So here it is. I basically assume that there is same this thing. Multiple vehicles are planning at multiple ways. Say a vehicle is coming here, a vehicle is coming, say this is the first vehicle here which is coming in this direction. There is a second vehicle somewhere around here. There is, suppose, a second vehicle which is also traveling, in this direction and out in this trajectory, and the vehicle being planned is here, which is traveling here. So while I am in this segment, while I'm planning for this segment, I see that this vehicle and this vehicle somehow happen to lie in the same segment. From this figure, it looks unlikely. So let's say it started here. These two are likely to have the same segment. Now from here I ask the question that if a collision occurs, if both occupy the center of the road or whatever, if a collision occurs between these vehicles, who is responsible? And clearly it's the fault of this side. So this vehicle has a low priority vehicle. I generalize this as a rule saying that if Ri and Rr are driving in the same direction, the vehicle ahead always has higher priority as compared to the vehicle behind, because clearly if there's a collision, then this vehicle would be held responsible. Suppose here this vehicle and this vehicle are using the same pathway segment at this region. I again ask the question, if a collision happens, who is responsible? Now the collision is happening at the left side of the road. If a collision happens at the left side of a road in two left driving countries, it's always the vehicle which is at the wrong side which is to be blamed. Which is what this covers. If Ri and Rr are traveling at opposite side, if it happens on the left, then this vehicle is right and this is the defaulter, and hence this has a higher priority, this has a low priority. If collision, instead this vehicle was traveling like this and this vehicle was traveling like this, and I was computing for this pathway segment. If collision happens on the right, then it is this vehicle's fault, and hence this has a low priority and this has a high priority. So this is a very simple prioritization scheme. What it enables me to do is that it enables me to embed simple traffic rules into such kinds of systems. And hence you can visualize in the previous diagram where multiple vehicles were traveling in who has a higher priority, who has lower priority. And I must say that in this layer, that a change in prioritization scheme would result valid outputs. It would result in traceable trajectories. It's just that they might not be as per the traffic rules. So that was hierarchy 1. Now, in general, we know that in a multi-vehicle scenario or in a multi-robotic scenario, if we only play around with the path and we do not play around with the speed, then what happens is there may be no output possible. And the very simple example of this is, of course, a very narrow road. There is a slow moving vehicle here, there's a fast moving vehicle here. There is nothing that how I can plan my path so that collision is unavoided. This way is not possible, this way is not possible. I'll have to reduce the speed. So as I said that I would be looking at planning of a single vehicle layer by layer. I'll be then generalizing the problem to the problem of coordination of with respect to multiple vehicles layer by layer. Similarly, in every layer, I'll talk about the speed adjustments. If it is not possible to plan for that particular layer, if it is not possible to plan for that particular hierarchy, then I need to do something with the speed so that I can proceed, else I won't be able to proceed at all. There is no feasible plan, and the speed adjustment principle is very simple. If there is this vehicle here and there is this vehicle here, and I cannot continue any further because of a collision with this vehicle traveling in the same direction. Now, even though I've tried this as a generic thing, you should remember that I'm dealing with the pathway level. So the vehicles would actually be in the center. At the pathway level, I always assume the vehicle to be traveling at the center of the pathway. So if I happen to collide with this vehicle like this, what I can simply do is that if this speed was v1, I fix my speed to v2, which simply means if I cannot overtake, I follow the vehicle in front. And similarly, if the collision was with some other vehicle out here, I would have basically reduced my speed iteratively. Then there's no, if I happen to collide with a vehicle directly in front, then there's a magic that happens that I can say if I cannot overtake, let me simply follow the vehicle in front. But with the other side, this does not hold good. I cannot come up with that magic number or magic speed. If nothing works, then I know that the road is blocked and I need to select a new route, which means I'll call the Dijkstra's algorithm at the highest level, at the route planning level, and do something. So that's all my pathway planning level. What you should be able to visualize, what you should be able to find out, if there is a pathway like this and if there are obstacles like this, there are vehicles here, vehicle 2 here and vehicle 3 here, then all at this level, where after I exit this level, every vehicle in its mind, it knows whether I go like this or it plans whether I go like this. It has some output in its mind, with which we come to the pathway distribution. And in the pathway distribution, I know that the work is very simple, that I have a pathway segment like this. I'll not draw the complete pathway, I'll only draw the segment out like this. I need to again ask the same question that I was asking at the pathway level. I again need to ask exactly the same question. How many vehicles are expected when I am here? I need to ask the same question. How many vehicles are expected when I'm here? Again, I'll be considering the same motion of the other vehicles that I considered in my pathway level, because you know that prioritization by pathway distribution level uses the pathway as the prioritization at the pathway level. I'll be asking the same question. How many vehicles are expected at the same level
how many different other vehicles are expected when I'm nearly here, and I'll simply distribute the pathway equally amongst them. So that's a very simple kind of thing to do. I again construct the same figure. I say that I have a road segment here. I have some vehicles here. Now this time let me do it layer by layer, or let me do it slice by slice, just to remind that my algorithm is slicing in nature. I already know the pathway, so I'm only drawing the pathway segments, and that's why the slices do not intersect the road segments ends. They only lie at the road boundaries. So for this layer, I ask how many vehicles would be occupying. Suppose I got the answer 3. So I'll suppose I got the answer 2, and the one which is myself, which is the vehicle being planned, so I divide it into 2. I need to distribute vehicles between them. So I knew basically V1, V2 and myself V were to be light here. I say I will lie here, vehicle 1 would lie here, vehicle 3 would lie here. I then consider this slice out here. I ask the same question, how many vehicles are likely to lie in the same region. Suppose this time I say I get the answer only you are I'm supposed to lie out here, so the I simply have complete autonomy over the complete road. I do it the same thing. It tells me that there's a vehicle V4 which is out here, so I place V4 here and myself V over here. So I'm getting the different snapshots of time. I'm getting the different snapshots, and I'm dividing road amongst them. Now V1, V2, V3 basically means I was at the center. Again, V means I was at the center. V4 means I was very much towards this end. There was some V4 which was out here. And similarly, I will trace this entire trajectory like this. You can basically, I've taken a hypothetical example. You can assume it what will happen with the other vehicles all around. So I'll divide this complete every slice I'll divide, I'll place in the vehicles, and I'll plot it as an X here, and I'll for visualization I'm simply drawing in lines over here. I'm simply connecting those X lines over here. So from now on I'll only be dealing with a particular slice of it. Particular slice of the vehicle scenario, or I'll be dealing with a particular pathway segment. So suppose I've got a pathway segment like this. I use two fresh notations. I know that the notations are being carried over from hierarchy 1, but forget about those notations right now. I'm consider them to be fresh notations. I will say there is a set H of higher priority vehicles. The priorities mean different things here. I'll set L of lower priority vehicles, and my distribution is such that all the higher priority vehicles come to the left of me and all the low priority vehicles come to the right of me. That is my definition of higher priority and low priority. Priority does not mean a conventional prioritization scheme priorities. They only mean whether the vehicle comes towards my left or they come towards my right. If it's by traffic rules, by general driving principles, if it comes towards my left, I'll call it higher priority. If it comes towards right, I'll call it my low priority vehicle. And once I've got my set H and my set L, which I'll query around all the other vehicles, I'll simply say that this is my line segment here. I know all the higher priorities vehicles, so for every higher priority vehicle I divide them equally towards my left. I place myself at the center and I divide the low priority vehicles towards the right. So all the H higher priority vehicles, the L low priorities vehicles, and one myself, the entire pathway segment will be equally divided among them. A very small catch here is that if I place the vehicles and I find out that so many vehicles have been scheduled that I cannot accommodate myself, I'll return infeasible. And if I find out that I'm unable to physically place a vehicle, then I'll basically try to move it a little left and a little right and see that if it still makes it feasible. So I'm trying to, although the general principle is that if this is the road, I equally divide my lines, I equally divide the road between H and L plus 1. So suppose H was 1, L was 1, so there were only 3 vehicles. I do this thing, but if I'm unable to place this vehicle out here, I'll try to move it a little left, a little right to see if it's still feasible. And if I still cannot find a feasible position such that it does not collide with the road boundary or obstacle here and the vehicle here, I'll simply return infeasible. Now, as stated, that in a multi-vehicle scenario, it is possible that my algorithm returns that whatever you do, there is no valid pathway distribution strategy. It can happen. And that's very similar to, I said that in a multi-vehicle scenario, if I cannot find a valid pathway, I need to do something with the speed to make it valid. The same thing I say with the pathway distribution strategy. If I cannot find a valid pathway distribution, if I cannot find a feasible pathway distribution, then I need to do something with the speed. I need to change the speed somehow. I need to change the speed so that my pathway distribution returns a feasible plan. And again, I use the same principles that I displayed at the previous slide. I change the speed so as to allow a vehicle to follow the another vehicle, and I completely call the entire algorithm once again so that as per the new set speed it may generate in a feasible plan. And the last thing is, of course, prioritization. I already said what is the motive of prioritization. The motive of prioritization is so that all the higher priority vehicles should come on the left and all the low priority vehicles should come on the right. So I generate in again random scenarios and I simply ask myself that which vehicle should come left and which vehicle should come right. So the first scenario is a scenario like this. If this is what the two vehicles, I know if this vehicle has to overtake this vehicle, it will always do it at the right. It's a traffic rule. It will never go left and overtake, even if I would have drawn it differently. So this is higher priority, this is lower priority for vehicles at the same side. For vehicles at the different side, now I know there's a two left traffic rule, so this always has to be towards the left of this thing. We never do that. We go or at the other side so much that we lie on the right hand side with some other vehicle also at the wrong side. We never do that. A vehicle always has to be at the correct side, so that means the left driving vehicles always have to be the left of the vehicles driving right. It's a two left traffic rules. So this is L. It lies towards the right. Remember, right is low L and left is low. And as compared to this vehicle, this low priority vehicle. So these are what the two prioritization scheme are, and they help in implementation of the basic traffic laws. Now there's a simple catch here that if you've been following, if you understand how the algorithm works, if I need to overtake this vehicle, what I'll do is that I'll go very close to it. I'm of course maximizing lateral separations, or I'm maximization separations over this line. So I'll go very close to it, then I'll make a very steep turn. I'll normalize myself, and after overtaking, I'll again make a very steep turn and I'll go. It will be kinematically feasible because there's another level of hierarchy which there's another level of the actual path generated at this level till this level of course will be this, but there's another layer of hierarchy which smoothens it up, which I'm yet to be which I'll be presenting in the next slide. But the problem is, even though kinematically feasible, even though traceable, even though the overtake would happen, it will not the two vehicles will not collide to each other. We know in general this overtaking would have happened like this, where not only the lateral separation was maximized but even the longitudinal separation was maximized. This in fact we when we actually simulated the algorithm, this is what we observed, and we thought that we need to do something about it to change it to this. So we floated in the concept of pre-preparation and post-preparation, which means if there are no other vehicle than the vehicle being overtaken and the vehicle following, then we'll try to shift the trajectory, or because I'm dealing at the pathway distribution level out here, so
at the distribution pathway level, in place of working out with this, I'll transform this into something like this. I'll make it smooth at the pathway distribution level. So there's a small tweak over the algorithm. And because overtaking is something very dear in our research, it's something that we discuss it. If I simulate three vehicles, the red vehicle, vehicle 1, which goes like this, the green vehicle which goes like this. So now imagine the trajectories of these vehicles. Imagine this vehicle is coming like this and this vehicle is coming like this. So these are two very different vehicles coming up from very different sides of the road. And imagine I let across a third vehicle, which is vehicle 3, out from here. So my third vehicle enters out over here. Now clearly one can see overtake would happen. I'll draw in a simplified version of this diagram here. My one vehicle was moving out here, my other vehicle was moving out here. If I generate in a third vehicle here, I'll nicely overtake like this. And that's what our algorithm exactly did at the pathway distribution level. Now remember when I said visualize vehicles moving at the pathway level, it was always at the center of the road. Now I say visualize vehicle moving at the pathway distribution level, it will always be at connecting the different snapshots of time that I generated. And I'll quickly walk through. Here there's no other vehicle than this vehicle alone, center of the road. Here I see that there's no other vehicle center of the road, but because of what I said pre-preparation, in order to smooth it up, I moved it here. Here there are two vehicles, vehicle 1 and vehicle 3, which is the vehicle being planned. The entire road distributed between these two vehicles. Again, there are only two vehicles out here. Now this vehicle starts going ahead of this vehicle. So afterwards it starts retracing its back. Here I'll say that here vehicle 1, when this vehicle reaches here, vehicle 1 is somewhere here. So vehicle 3 will not consider vehicle 1. In fact, it's much behind. But now it starts seeing vehicle 2 out here. Now vehicle 1 and vehicle 2 are out here. So I need to distribute this pathway between vehicle 1 and vehicle 2. Vehicle 2 obviously has lower priority than vehicle 1. So I select this for vehicle 1 and this for vehicle 2. Again here vehicle 1 and vehicle 2 are nearby. So this would still have a higher priority. This would still have a higher priority. It will be towards the left and this vehicle would be here. And when I go to here, vehicle 2 is far away. So I basically occupy the center of the road. And the last trajectory, the last hierarchy, which is a very simple trajectory, I don't want to go through or such extensive discussion in this. It simply says, when I simply connect the snapshots of time that I had been doing so far, when I simply connect them, what happens is that they are such ugly in nature, they are discrete in nature. A vehicle cannot make such a sharp turn right from here to right from here. It cannot make such a, so I'll firstly need to smooth it up. While smoothing it up, while smoothing this trajectory, I may notice that the smoothed trajectory is has still such sharp curves that I cannot by the kinematic or by the non-holonomic constraints, I cannot trace the trajectory. So it will try to optimize it up. It will try to optimize it enough so that the sharpness is reduced. So from here I get into something like this, or from the smoothened version of this would be this, or from here I get into something like this. And how it will do, it will find consecutive points where the trajectory is very unsmooth, it is very sharp, and I'll simply place this at the midpoints of these 2 points if I can. And thirdly, it is possible that the trajectory is infeasible. I mean, I basically generated the random snapshots. It may not always be possible to connect these snapshots. What this figure does not show that they are all the other different vehicles, but they would be other vehicles. If I smooth it up, maybe I'm causing collision with another vehicle. So it makes infeasible. It tries to make infeasible trajectories feasible by small local search. If, by the way, smoothing is performed by spline curves, if I still cannot find a feasible trajectory by using a small local search,
this is something that I have repeatedly for every hierarchy. I've said if I cannot find the feasible pathway, I reduce the speed, I fix the speed. If I cannot find the valid distributed pathway, I fix the speed, I reduce the speed. If I cannot find the valid trajectory, I'll say if there's a lower level, if the collision is with a lower priority vehicle, then obviously I do not consider low priority vehicles. The low priority vehicle has to do something to make it feasible. If there's no low priority vehicles, I basically again fix the speed using the same norms. So that's what the trajectory generation is all about. And this is what this is what basically the previous slides I've shown you the basic distributed pathway and the pathway level. Here there is no other vehicle, so I've shown this path at the pathway level, which will be the same for the distributed pathway level because there's only one vehicle. And you see that the trajectory then was not smooth, and this has been smoothened, and this is the overtaking trajectory. All these three vehicles, the trajectory has been smoothened. So if I just go back, the distributed pathway level trajectories which are here, now these trajectories are completely intraceable, but if you go here, the separations have been compromised. They are no longer maximum possible separation, but the trajectories have been smoothed and they are now traceable. And the last thing that I would like to say is that there's another little tweak in the algorithm that when I reduce the speed, I basically reduce it permanently, which means that if there is a vehicle in front and I cannot overtake this vehicle, I'll obviously follow it. I cannot overtake it because I'll cause collision with this vehicle. The problem with the algorithm presented so far is that I'll always follow it till the end of the road segment. There has been a little heuristic used that once this vehicle has passed, or once the lateral position of this vehicle changes by a large amount, I basically replan in order to make a overtake which was first infeasible and later feasible, in order to make it in order to make the overtake possible in the same road segment. So there is a little tweak that has been done in the algorithm. There's a little heuristic that has been used, that I know that a vehicle going, I need to replan this. I know when to replan this vehicle, and by replanning as per the change scenario, an overtake is possible. The speed is again restored to the maximum amount and overtake actually happens. That is what I showed in the results page. In the when the vehicle initially could not overtake, it later increased its speed and actually overtook the vehicle. Now there are some analysis involved. I'll not go into the depth of it. What they basically means is, if I increase rho, basically the vehicle can make very sharp turns at very high speeds, and because of that, basically initially when rho is very small, the vehicle cannot at all optimize its trajectory. It's not at all possible to find an optimal to trace a trajectory. It's basically saying like you cannot turn at all. So my local optimization algorithm simply fails in this region, and the path length is high. It works well in the middle region. In the very high region, what happens is that very sharp turns are allowed, so there is no use of locally optimizing the trajectory, and therefore my local optimizer does not work at all. It says that you can, even though the trajectory is very steep, you can turn, and therefore I'm useless. Let me not perform any task and save time. And that is again what you see in my higher region. My local optimizer takes zero time for optimization, and lower end it's planning, and after that it simply leaves away. It simply fails. It simply says maximum time reached, I cannot do anything more. And high value of rho basically enable higher speed possible, and that's what happens. Low value of rho, the vehicle will have to basically really, it cannot make any turns sharply, so it will have to go very slow. We know that if rho increases, then the vehicle can make very sharp turns, and because of that, my time of travel decreases higher up towards the end, and very low it will have to reduce its speed very much in order to make travel feasible. And similarly, if my sweeping line, if the distances are very far apart, then basically I have got very few points for local optimization. I only, like in this case, I only need to optimize 4 points. So my time required for optimization will be very low, while if I the sweeping line is very close to each other, there'll be hundreds of points like this, and I'll take forever to for optimization. And this is the scalability. Obviously, if the number of obstacles increase, the time to optimize increases, a lot of time to do, and the number of vehicles increases, the time of optimization increases, which is a proof why the algorithm, how much the algorithm is scalable. So it cannot, the algorithm currently cannot have hundreds of vehicles. It can only have some vehicles. It can only cater to the needs of some vehicles, and similarly, it cannot have a wide range of obstacles. An exception, of course, which I didn't present to make the algorithm simple, is that if one vehicle decides to overtake to follow the other vehicle no matter what, so if it's the speed is reduced, I never consider this vehicle in the planning of this vehicle. There's no way they can they can collide. So once I say that this vehicle will follow this vehicle, I simply delete this vehicle from the planning of this vehicle. The one problem was that many times it said that I'm close enough and hence place me in a new lane, which is useless. They are following, they should be following using the same lane. The other thing is that it makes planning computationally fast. So I simply delete this other vehicle, and that will be all for the presentation. Thank you.